Okay, so a little bit of info about how to find us on the web. You can find us on Twitter at Influx, and of course you can Google us and find us. You can find me at my Twitter handle there, or you can email us. So to start with, who's heard of InfluxDB? That's good. All right. I mean, prior to seeing it on the program. Is anybody using it? Great. Experimentally or actually in production? Production. Okay, good. All right. So, instrumenting a data center. First, let's get a high-level overview of what we're talking about here. We have musical instruments, and we want to get those into your data center. That's what we're talking about. All right. So the real problem is you've got dozens or hundreds or thousands of servers, and you need some way to efficiently monitor those servers. These could be in a single location or geographically distributed. You got many things that need to be measured to keep this data center up and running healthy, and all the applications in it. Network loads, CPUs, memory, disk, many things. So the solution is we automate it, which is easy, right? So we automate. What are we going to automate? We need to automate collection of the data. We need to automate storage, analysis, and alerting. So we'll just write a few scripts, a few hundred lines of Python, we'll dump the data into SQL, and we're done. But let's take a look at a few examples of what happens if we try to do something like that. And it's not that it can't be done. It has been done. But I think it can be painful, and there may be better ways to do it. So if we take an example with a single server, we're going to take 100 measurements from it, which is a conservative number. We have users taking many more than that per server. And you take these measurements every 10 seconds, 365 days a year, you'll end up with 300 million records, or as we call them, points. So that's manageable, but it's still a lot of records, and it's only a single server. If you make it 10, no surprise, it goes up, 3.2 billion. So things are starting to get a little bit ugly now if you're trying to dump that into a SQL database. And there are ways, I know there are ways to deal with that in SQL databases, but we're going to continue on and down this road of examples here. This is common. It's not, some of you are maybe looking at this thinking it's ridiculous. I'll never have 2,000 servers. I'll never need to take that many measurements. Others of you are probably looking at it thinking, yeah, that's a pretty small number of servers. But this is a realistic number. This is something that we hear from users all the time. We have 2,000 servers, or we want to take this many measurements per second. Some want to take many more measurements per second than that. Others want to take more than 200 measurements per server. Some people have more servers than that. But anyway, in this example, we end up with 2.5 trillion records. So good luck with that in a SQL table if you try to go that route. And there are other problems also with this. It's a very high write load. And it's also common in this use case to have as many deletes as you have writes. So some of these characteristics and other things make this use case not really ideal for SQL. But a time series database is ideal for this kind of database, or for this kind of workload. So now most of you raised your hands and you've already heard of InfluxDB, and you're already familiar with time series data, but I know there were some hands that didn't go up, so I want to do a quick run through of what a time series actually is. It's at the generic, no particular database level, just at the concept level. Time series is really simple. It's just values and timestamps. You'd measured something and you'd measured it at this time, and you're going to store that value. So, arranged in a table format like you might store it in SQL, it's just just looks like that, timestamp and value. And so in a single series, in a time series, would just be a stream of these things, values with timestamps. So that could be anything from CPU usage taken every 10 seconds to cumulative steps taken if you're, for a fitness tracker that you're wearing on your wrist. Could be happy InfluxDB users over time. We hope it's shaped like that. So you take a whole bunch of these individual time series and stick them in a database, and that's, at a high level, that's a time series database. And data center metrics fit nicely into this model because we have, dozens or hundreds of servers, and each one of those has multiple cores in it, and you want to measure say the CPU usage from each one of those cores. That turns into thousands of little tiny streams of data or series of data. All right, so let's look at this, and we're going to kind of go. There was a slide earlier that listed out the things that we need to automate: data collection, data storage, analysis, and alerting. But we're kind of going to go out of order. Influx is the database is kind of at the core of this, so we're going to start with that, and then we'll look at the peripheral pieces of it later on. So InfluxDB time series database. It's written in Golang, Go language, which is from Google. So it has no external dependencies. It compiles to a single executable. Distributed and scalable. So those of you that use it know that the distributed and scalable part is a work in progress. We do have users that are running clusters, but it doesn't scale up to tens or hundreds of nodes in a cluster yet. We're still working on, in the query engine part of it, getting the queries to run. The data retrieval, most of it does work as distributed queries now, but some of the meta queries we're still working on those. Easy to install, use, and maintain. Those of you that already are using it or installing it hopefully could attest to that. The ease of installation is generally, especially just if you're looking to get started with it and try it out, installation is very quick, typically just a few minutes to install it and have it up and running. It's completely open source. You can find it on GitHub. If you Google for Influx and go to our website, you'll find links to our GitHub repo. It's very active open source project. We've got about 8,300. It's been going for about 2.5 years. We've got about 8,300 commits to it over that time. And we've got about 172 contributors. It's regularly, there are regular updates to it. Mentioned earlier, written in Go, which is also open source, a great language, if you haven't looked at that. Some of the features of it: SQL-like query language, which is great for almost everyone's familiar with SQL. So coming into InfluxDB, this makes it easy. HTTP API. We support other protocols for ingesting data other than our own. And we're going to talk some more about that later on. Automated data retention policies and aggregating on the fly. So let's actually, we know what type of data we're storing coming from the data center, metrics data. Let's look at the model that InfluxDB uses for storing this data. Now this, at the top, I've got an InfluxD daemon, which is actually, of course, not part of the data model itself, but I put it up there at the top of the thing just so we can kind of see where things fit in. It's a single running process. There's no other peripheral processes that need to be running. And a single daemon can manage multiple databases. Then inside of a single database, and this is where we start breaking it down at a very high level to how things are stored, or the conceptual pieces that are inside the database. We have measurements, like we talked about earlier: CPU usage, memory usage, disk usage. And this is actually, if you look through our documentation, we have a glossary. These are the terms like measurements that you'll see in the glossary. So a measurement it's something you're measuring: CPU usage, packets received, could be whatever your temperature, steps taken, anything. And then when you take one of those measurements, it's important to know where it came from. If you've got a CPU on server A, a core running on CPU A or server A, and one over here on server B, and you take measurements from both, and you don't write down where that came from, and you drop them both into the same bucket, you come back later, you can't figure out where the measurements came from. So that's what tags are for. You take a measurement and you tag it with where that data, where that measurement came from. So in the example here, country equal Germany, DEU, and region equal Northeast. So that gives us an idea of where a measurement would come from, and we call those tags. So if you combine a measurement and a unique tag set, that gives us what we actually inside of Influx call a series. And you remember a series is like a single little stream of data, like measurements coming from a single core. That would be one stream of data or one series of data. And so just another example of the same, separate, a second series. So, and I don't know if this may be too small to read, but then we have points, which are the actual values themselves. If you measured the CPU usage and it was 33%, then that's a point. And that measurement, or that point, was collected at the time with a timestamp, and it's got its, the tags associated with where that measurement came from. So that kind of takes us from the top down to the lowest level. We got measurements, tags, series, and points. So let's look at what's indexed. Sometimes people that are new to it get confused with, they'll store values and tags, or tag things that should be tags and values, and I think it helps to understand how Influx handles indexing, so that when you're deciding where to put a piece of information, whether that should go in a tag or into a field. So we have metadata, which describes the data, and so measurement names. These are all things that are going to get indexed. Tag keys and values, field keys. So, and sometimes if you're new to Influx, this is also a little bit of a source of confusion between field keys and field values. But so that would be, often we just call it value, but you can actually have on a single measurement multiple fields, and that's not uncommon. If you were storing, let's say, events for user clicks, you might store the X and the Y coordinate as separate fields for the click. So the actual value, so in that example, the field names X and Y would be indexed, or the field keys. But the field value, like the actual number of where you clicked for any one particular click, that value is not. So it's just the field keys. And so this sort of seems like maybe a contradiction of what I just said, that field values are not indexed. They're indexed by time. And I have an asterisk there because it's not indexed down to a single point. If you say, but what you can say, what is indexed, is if you have a select query and you say where time is greater than now minus 1 minute. The engine can quickly look up what file on disk or what shard on disk that data, where that time period. It knows it can calculate that time period quickly and figure out which file on disk or which shard contains that range of time. So that part goes pretty quick. It can narrow it down, but it's not a perfect index that doesn't know exactly where to look in each shard file. but it's not, if you have a string field, the string field values are not indexed. This is also another important point. It rarely causes any issues, but typically where it causes an issue is somebody spins up the cheapest DigitalOcean instance with the least amount of memory in it, and they just start hammering it with data. And then you can run out of memory if you do that. The index is held in memory, which I guess we could talk about a little bit. This is both important for the speed of the write throughputs. So every time a point comes in, it quickly has to figure out which shard on disk it has to be written to, and it has to figure out which node in the cluster owns that shard. It doesn't have time to hit the disk and figure this out, so this index is all held in memory. When it sees a point, it can quickly look at the measurement name and all the tags, get a series ID from that, and then from the series ID and the time range, it can quickly say, okay, that belongs in this shard, and route the data that direction. So that's one of the reasons that the index is held in memory. And there are a couple other reasons that are probably a little less significant, but that's the main reason is actually for write speeds. Let's look at what's not indexed. Field values by value, which I kind of mentioned earlier when I was talking about field values by time. So in this example, we say where a value is greater than some number. For this query, it actually has to find the shard or shards that the data may be located in. And then it has to go through every point in there looking to see if it satisfies the condition. And also not indexed is metadata by time. This is generally not a big deal, but advanced users of it will sometimes attempt to do like a show measurements query and say where time is greater than. And that would be useful. Maybe someday we'll implement that. But the problem with that is that in order to do a where time clause with a metadata query, we actually have to go out and hit the disk, and that makes that lookup much slower. Currently, all the show queries allow you to explore metadata without actually hitting the disk. And actually, I should have had a slide in there. Before I move on to data retention, I'm going to go back to the metadata for a second. One of the useful things about this, the show queries, is that in this type of data, it's schemaless, and you don't always know what measurements you're going to have, what tags you're going to have, tag values you're going to have. So a common need is to actually be able to explore the data. So you can run a query. You could run a show measurements query at 1 minute and get 10 measurement values or names back. But in the meantime, before you run that query again, if something else happens to write in a new measurement on the fly, the next time you run that query, then you're going to have new measurements. And the same thing could be true for tag keys, tag values. So it's important we have an API through the query language that you can explore what data is actually available. All right, so let's talk about data retention. If you've got a lot of servers, you've got a flood of a waterfall of data pouring into your database. And so you probably need a strategy for aging this data out because disks usually don't run out of space at 2 p.m. on Wednesday. They usually run out of space at 2 a.m. on Saturday. And usually this data, the full resolution data, it doesn't need to be retained forever. If we're looking at packets received, it may be important or useful to have, the full every 10-second count of packets received, and you may want to store that resolution, every 10 seconds for a week or for a month or some relatively short period of time. But a year from now, the number of packets that were received having resolution at 10 seconds is probably not valuable. So you need to, typically you want to downsample and age that data out. And so we have retention policies to help us with this. So let's look at how those work. All data, when it's written into InfluxDB, is written into a retention policy. Now, if you don't specify one, it gets written into a default retention policy. When a database is created, a default retention policy is created automatically. It has an infinite retention period. And then, by default, all rights go in there. You can modify that default retention policy, change the name of it, change the time of it. You can create all your own retention policies with any retention period that you want. And you can change which one is the default. Each policy has a duration minimum of 1 hour, and then all the way up to infinite. And the database monitors these in the background. So once you've created a retention policy and you start writing data into it, you no longer have to worry about deleting old data. If you've set the retention period to an hour, it's going to handle that for you. Data that's beyond the retention period is automatically going to get deleted. And it handles that efficiently because as it reaches the end of a retention period boundary, it starts a new shard file on disk. And so once the old data ages out, it just simply has to delete a single file and all that old data is gone. So that makes the deletes very efficient. And that's all happening in the background. And so this is an example of how you might age data. You've got on the left side there what I call a raw retention policy, which is just a name I gave it in the example, with a retention period of 1 day. So this would be probably very high resolution data. If you're only going to hang on to it for a day, that probably means there's tons of it coming in, or it means it has no value after a day, or at least not at that resolution. So you can run a query, select into query. So there we're calculating the mean. We're pulling it out of from the raw CPU measurement, and we're selecting it into the mean of it into the CPU 1 hour retention policy, which actually the name may be a little confusing there, but you can see that the group by clause is 1 hour. So the mean is what it's doing is it's taking the data points 1 hour, all the points in this 1 hour segment, calculating the mean of it, storing it in that retention policy. So it's rolling, it's downsampling an hour's worth of data into a single point, and storing it in a retention policy, which we're going to keep for a week. And you can also see at the bottom it's got shards. So the shards in InfluxDB actually belong to the retention policy, and the retention policy service that's running in the background will delete those shards as it needs to. All right, so that's cool. We've got retention policies. You could connect using the CLI and run a query and downsample the data into an older retention policy or to a longer term, lower resolution, longer term retention policy, and it'll, the retention policies will handle cleaning up your disk space for you. Or you could write a external script to do that for you, but that's a pain. You don't want to do that. What we really would like is something that just automates that downsampling also. So we have continuous queries, which are just queries that are stored. You can tell it, here's the query I want to use to do the downsampling, store it in a database, and run it automatically for me. So that looks roughly the same. It's a different command. You just tell it to create a continuous query, give it a name, tell it what database it belongs to, and then it's basically the same query that we had in the previous example, except that I've removed the where clause from it because you don't need that in a continuous query. And the reason you don't need the where time is greater than or whatever is because the continuous query service that's running in the background generates that where clause with a time frame in it on the fly based on a couple of configuration settings and the group by time that you have there. And so what it'll do is just, every time it sees that this query is due to be run, it will say, okay, calculate for the current hour and store it, and then it'll back up typically by default, to the previous hour interval, recalculate that one and store it, and then it'll by default also back up and calculate one more into the past. And the reason it does that is to pick up lagged data. So if in your scenario or in your use case, data comes in and it can be, it can come in a few minutes old, like you're getting a point for the current minute, but then all of a sudden a handful of points come in for 10 minutes ago. This continuous query, by default, the config settings will pick up that older data, recalculate your summaries for you, and they'll stay accurate. If you never have lag data, you can change a config setting and tell it, don't bother recalculating old intervals. I won't talk too much about replication. It's not, I don't think, all that interesting. It's handled through retention policies. When you create a retention policy, you set a replication for it. I'd have to check. I didn't write this, I haven't worked on this part of the code, but I think we currently only support full replication. I think that's right. I'd have to look that up. Meaning that if you've got 3 nodes, replication factor should be set to 3. So let's look at some of the functions. We support functions for data manipulation and analysis. And they come in several different varieties. The first is aggregations. So this is aggregations which would condense data. You could tell it to count all the points that may meet a certain value, and it would go through and count how many there were, and you'd get back a single record from all those points. With just the count distinct, or you can get back distinct values, calculate means, medians, and sums. Then we have selector functions, which kind of, as the name selectors would indicate, it just pulls out a set of points based on the function and the parameters that you pass to the function. And then we have transformations. And so an example that fairly common one is the derivative. Let's say that you've got, if you're looking at packets received, and it's the total number of packets received. So every time we take that measurement, this time at this minute it was 10 packets received, and a minute later we check it and it was 100 packets received total. So that's just a constantly, if you were to plot it on a graph, it's just constantly going up and to the right. But what might be more interesting is to look for that measurement is to look at the derivative of that, so you can see the rate of change. That may be what you're more interested in, is to see if there are spikes in the speed at which the packets are coming in. All right. So let's talk about, that kind of summarizes at a high level how InfluxDB, the data model, how data is stored, it's indexed. I didn't mention, sometimes we get asked if we can create an index. Right now we don't support creating any other indexes. It's essentially, if you want to create an index, you store it as metadata, and it will get indexed. But we don't support telling it to index on a field value. So at a high level, that's how we store and index and manage data. So let's talk about, now we're going to move in the slide that we looked at earlier where we showed the different pieces that we needed to automate. We're going to move out to the left and look at data ingestion. How do you get the data? You got a place to store it now and manage it, but how do you get it in there? So with just the database itself, we support several different protocols that are already out there. So if you're already using CollectD or writing data in open TSDB format or Graphite, we support, these are plugins that are actually in InfluxDB that you can enable through configuration. And it should just be a drop-in, Influx should be a drop-in replacement to consume those protocols. This is what we recommend. It's I don't know if the link in blue shows up very well there, but if you go to our GitHub account, InfluxDB, you'll see that we also have a project called Telegraf. Can you guys read that? You can't. Sorry. All right. So it's just github.com/influxdb/telegraf, and it's spelled the way it is up there at the top. And so that's another open source MIT licensed project that we've got that's also written in Go. And its purpose is to collect data. You have your database installed somewhere else in your data center. But then you can install Telegraf on the servers or any other thing that you want to collect data from. And it's plugin based. We currently have, I think it's roughly around 30 plugins for measuring various things like system stats, different databases like Postgres, MySQL. You can measure some stats from those, Redis, RabbitMQ. There's a bunch of them out there. If you want to see all the different services that it's capable of collecting data from, you can go out to the GitHub and look in the services folder, and you'll see all the plugins there that it supports. And they're probably listed out in the documentation for it as well. So also written in Go, cross-platform. I'm not sure actually if we have a Windows build for it yet, but we were just talking about this recently internally. Do we have, how many are Windows houses or systems? Mix? Okay, some. So we do, if it doesn't currently compile and run on Windows, I know I don't work on the Telegraf project, so I don't know if it's actually compilable and runnable on Windows at the moment, but I think if it isn't, it will be soon, because that's an important goal for us. And it's also designed, we welcome community contributions to this. Many of the plugins that we have, it's a new project, but there already plugins are coming in from the outside, and we welcome that. So if any of you, if you look at Telegraf as a possible solution to monitor your current system, and there's something missing, you can either talk to us about what you're looking for, and if it's on the radar, we'll let you know, or you can develop it yourself, and we would love it if you submitted a PR for that. We also have client libraries. This is not a full list by any means. Go, of course, which is we use and actively maintain ourselves. There's Ruby, there's Java, Python. Go is the only one that I've worked on, and I can't remember. Some of them are community contributed libraries, and some are ours, and I can't remember which ones are which now off the top of my head. Go is the only one I've worked on. But we have these libraries. And this is if you know, if for whatever reason Telegraf doesn't meet your needs, or you're not already using, you know, CollectD or Graphite or one of the other protocols, and you have some custom need and you want to roll your own, then there are, you know, dozens of, they're not dozens, there's probably a dozen different client libraries for InfluxDB. And then if that's still not good enough, or you don't like a particular client library for your language, or you can write your own. I mean, you can write your own client library, or you can just directly write to the database. I've, you know, for my own debugging purposes, written shell scripts that, you know, run top and IO stat and things like that, that, you know, poll that and write the data into the database. So it's very easy through the HTTP API to write data. And I've got a single little line, you know, example line there. It's a text-based protocol. Like, you can write data in using curl. And that's an example of what the actual data looks like. Over on the far left, CPU, that's the measurement name. Host is a tag key, and then server A would be the tag value for it. And then value equal 10, and then some bogus, ill-formatted timestamp there. I just typed in some numbers. But that's it. That's the format of the data, and you can create multiple lines of that. It's easy to build it up in any language typically, or even shell script, and write that into the database. Visualization. I don't actually have a running demo of this today. I wish I had, but I don't. Grafana is it's an open source, very popular dashboard that interfaces with InfluxDB. If you haven't used it, take a look at it. It's very easy to configure and get working with Influx. And then we also have our own that we're developing in-house, which is going to be a closed source product. I think there's going to be some open source exhaust from it probably for people that want to develop their own applications that you know, render graphs of time series data. But we're also, you know, our main goal is to provide a product that does this. And we get questions, and there's been, you know, a little bit of tension with the Grafana community over it, but our intent is not to not support Grafana. We're going to continue that. We love Grafana. We work with those guys. We're happy to, you know, fix issues and make changes to keep that working well. But Grafana works with multiple other backends, and like most things that do that, it can't focus on, you know, it can't take advantage of every feature that Influx has, and so we wanted to develop our own that does that. It's in its early stages, still in the beta stages, but you can, from our website, you can find a link to register and download a free, you know, demo of the beta to play with. This is actually, this little GIF that's playing is old. It's out of date. There's more features to it now. Now, I don't have a slide for alerting yet, but that's on anybody that's followed us closely knows that, you know, Paul, our CEO, has talked about the TICK stack, or TICK. The T is Telegraf that we looked at. The I is Influx. The C is chronograph. And then there's going to be a K piece, which he's, you know, talked about being the alerting piece. That's not out yet, but keep your ears open. So that there'll be an announcement for that coming pretty soon. And that's it. That's all I have. Does anybody have any questions?
Regarding comparing to TSDB also uses tags and has a GUI interface that lets you decide which tags you're going to. It gives you a lot of flexibility in how you view your data, which you can't really do with Grafana. Can you do it with Telegraf?
So I haven't used OpenTSDB. So when you say view the tags, like on the graph, or?
So for example, if you have 5 different tags, and there might be data center, user, project, you don't really know what data you're looking for. You go to a GUI interface and you say, well, okay, I want to just look at all the projects.
Oh.
Look at these 2 projects. You don't have to create a new dashboard image that says, you can all do it all from one screen.
If I understand what you're asking, then I think so. So the question is will Chronograph have a GUI that allows you to see what tags are available? Yes. So it's, I don't know if it, yes, it probably doesn't show up very well in this animation, but yes, it queries the database in, pseudo real time to get a list of measurements, get a list of tags, then get a list of tag values. You can, I think you can filter by like regular expressions on that stuff. I don't know if that feature is actually in the demo version yet, but it's been kicked around. I think that's being worked on. So yeah, so that's an important part of it, is being able to explore the data. Like we talked, I was kind of talking about that earlier in the Influx part of the presentation. You don't know, it's schemaless. So at 1 minute, this tag may not exist, and the next minute it may exist from data that comes in. And so yes, it's important for a visualization tool to be able to explore the data and see what's currently there. And it will have that. Next. That's a good question. The question is, are there types in the values in the database? And the answer is, the first time it's written in, no. But then once you write it in, that field is always that type. If you try to write in again with a different data type, you'll get an error.
What are the types?
Yeah, ints has been one we've bounced back and forth on, and I can't remember the last decision whether we took. I think it still supports ints. But floats is the primary. We support string, bool. There's been discussion of like a byte array. I'm not sure if that was in there at one point. I'm not sure if it's still in there.
For continuous queries,
Oh, sorry.
do you have to create a new continuous query for every, let's say you have 200 metrics, do you have to create a new one for every single one, or is there a way to say like,
There is. We just added a feature. We call it back reference. It's probably a bad name for it, but you can, when you create the query, you can say select into my retention policy : measurement. And then you can in the from, you can have a regular expression. And so whatever the measurement names that match that regular expression, it will create that same measurement name in the policy. I can show you that syntax afterwards if you're interested.
So I think we've got time for one more question because we're running a bit over.
But
You said that tags were indexed. Does that mean tag cardinality has no impact on query performance?
I won't say that it has no impact on it, but it's.
It has to be just a metric, so you get a lot of tags.
I mean, there's a limit to it, and the answer to that probably is more of a Go language specific thing, because we were using maps for that. And I think somebody recently showed, I haven't tested this, so I don't know, but somebody showed recently that Go maps aren't actually constant time. There was some, maybe that got disputed, I'm not sure, but there were some interesting graphs there showing that Go maps weren't actually constant time lookup.
Is there locking issues then with writing and reading if you're using that?
No, it's not really, it's not a locking issue problem. The bigger issue with it would be like if you were trying to store GUIDs or something in there, then your cardinalities is going to grow out of hand, and probably bad things would eventually happen. But that's the kind of data that shouldn't go into the tags anyway. I think that's it. Thanks, everyone.
Thank you, folks.